In this tutorial, we're going to talk about how a half-wave plate affects the polarization state of an incoming beam. And we're going to do this in a couple of stages. Let me start with a very simple sketch that gets at the heart of it. Suppose we have a wave plate, and I'm going to draw it having a square cross-section, as many of them do. And a half-wave plate, as we saw in class, has a Jones matrix, which we'll write as 1, 0, 0, minus 1. And we could also think of that or as 1, 0, 0, and then the phase shift of pi radians. E to the I pi, of course, is minus 1. And sometimes we think about it this way just because in this particular place of a half-wave plate, it's easier to think about a minus 1. There are two axes, and I'm going to label them with little tick marks here. So that's the one axis. That's the x component of the light. We're going to multiply that by 1. And then along the other axis, we'll call that the minus 1 axis of the wave plate. And that is the y component, the vertical oscillation of light, the electric field. And we're going to multiply that by a relative amount minus 1. That's how we say that the y component has acquired a pi phase shift relative to the x component. So when I do that, I'm going to draw a dashed line along the 1 axis. If we now send in an input polarization state, again, this is the x-axis here, just to make sure that's completely clear. This is the x-axis, and this we will call, say, the y-axis in our convention. So if we are to send in a polarization state linearly polarized, say, in this direction, let me put, although it's oscillating back and forth, let me put a fat filled-in arrowhead here so we can keep track of where that arrowhead is going. And what I'm going to show you mathematically in a little bit is that if you have an oscillation that goes like this, if you want to know what the output polarization is going to be once it goes through the wave plate, what you do is you look at this angle here, and you just double it, move the arrowhead down to there, and you will get this oscillation. This is the orientation of the output light. So let's make sure to label that. So this is the in state, and this then would be the out state. So rotating through, you reflect the light across the 1 axis, and that tells you the orientation of that light. We'll derive that mathematically in a little while. I just want to also say, suppose, however, suppose we had the alternative case. I'll draw that off to the side here. If instead we had a wave plate where we rotated the axis by 90 degrees, so that we then have the 1 axis up on top and the minus 1 axis now on the side. And if we sent in the same state to that, so again we've got a big arrowhead over there, what will this state do? This wave plate has a Jones matrix given by minus 1, 0, 0, 1 clearly. We would draw the dashed line along the 1 axis here. We would calculate now this angle and reflect here, and we would now get the big arrowhead to be over here. And that would be the output state here, where this again is the in state, and this over here is the corresponding head of the arrow in the out state. Even though this out state looks different from this out state, notice that the orientation with respect to space is actually the same along this state and this state. We'll talk at the end of this tutorial about how they're out of phase with each other by 180 degrees, but if all we want to know is what the polarization is, the polarization of this state, the shaking and the linearity of it, is the same linearity and shaking direction as this state. And if this is the only light that I'm measuring, my detector won't be able to tell the difference in their powers. So, take-home message about wave plates is that you draw a dashed line along the one axis and you reflect the linearly polarized light across that axis. Now let's dive into the mathematics a little bit and see how that gets supported. So now I've drawn an optical system here, an optical axis, a light source shining light this way, and I've got a half-wave plate, I'll write that as HWP, half-wave plate, placed here in the middle of the system. So we can consider the polarization state of light at some position here on the right-hand side. Let's call that position A. So let's suppose that the light is linearly polarized. If I look at the polarization state of that light head on, maybe it looks like this. Linearly polarized light. There's the head of the arrow and the unfilled tail of the arrow. And then let's suppose it goes through a half-wave plate. Well, what's the state look like, first of all, at the beginning? Our standard language for this is to talk about the angle that the light makes with the x-axis. We're going to call that angle theta. So the x component of this light is cosine theta, the y component of this light is sine theta, and that means that the state at A, if I now look at the math for this state, the Jones vector is cos theta sine theta. That's the input state. The Jones matrix for the half-wave plate, as we just wrote and as we've seen already, is to multiply the x component by 1 and the y component by -1. So that's going to equal something. We can now think about what the polarization state's going to be at B. First, let's remind ourselves what we saw in the initial sketches of this tutorial. Well, the half-wave plate, the x component of the half-wave plate, the x orientation is what gets the 1. This is our horizontal x-axis here. So if I have an input state making an angle theta with the horizontal, then our output state here is going to make this angle negative theta with the horizontal. What does the math say? If you do the matrix algebra here, you get a state which is cos theta, 1 times cosine, 0 times sine. And this mathematics, 0 minus 1 times cos sine, gives me minus sine of theta. And that can be written as equal to cosine of negative theta, sine of negative theta. So I now have an output state here. That's the output. And an input state where cos theta sine theta has become cos minus theta sine minus theta. I've got theta in going to minus theta out, which is exactly what we were saying visually before. If you have a positive angle theta made with the one axis on the way in, then this half-wave plate in this orientation is going to give you a minus theta linear orientation on the way out. Now let's consider what happens if I rotate the half-wave plate. So I'll do a little bit of erasing. Okay, so what's different about this situation now? I'll emphasize that by writing it in yellow. Is that the half-wave plate, the minus one here, and the positive one here. So now let's think about what the polarization state is going to be. How do we figure out what it's going to be over there? Our rule is to write the wave plate. There's the incident state along this direction with its arrowhead, solid arrowhead there. Where's that solid arrowhead going to go? Well, we want to keep track of the one-axis. And remember, this is now the one-axis. So we reflect about the one-axis, and we get an output state over here. There's the output state with its arrowhead over there. So we've gotten a rotation to this position, which looks like it's out of phase with rotating this way. Because instead of the solid arrowhead going to here, the solid arrowhead went to here, but the oscillation is along that direction. So let's see what the math is telling us. Fit these two things together. So the math is saying that we are now going to have an output state here of, now it's minus 1 cosine and 0 sine. That's minus cos theta. And then it's positive sine theta. And that can be written, if I pull out the minus sign, I'll even write the minus sign that I'm pulling out as e to the I pi. And what's left inside? Now I'll have positive cosine theta and negative sine theta. Well, wait, that's just the state I had before. I can now write that as e to the I pi cos negative theta sine negative theta. So now that is my output state. That's my output. And what you see is that we get the same effect, that cos theta sine theta state becomes a cos minus theta sine minus theta state. We have theta on the way in, again going to negative theta on the way out. The only difference is that we pick up an extra global phase, and I'll just emphasize you for your notes, that's global phase of e to the I pi, which is not influencing the overall polarization state and wouldn't influence a measurement of that state if there's no other light in the situation. So now we've done it. We've run the mathematics of a wave plate either with the horizontal axis being the one or the vertical axis being the one, and we've seen that the polarization state in either case reflects about the one axis, and actually you don't even have to remember which one is whether the one axis is vertical or horizontal if all you're interested in is the sense of polarization of the output state, because a reflection this way that we've drawn here gives you the same orientation of a linear state as if you would reflect it about the horizontal axis. Now, so far, this entire discussion has only asked what a half-wave plate does to a linear input state, where the x and y components are in phase with each other, where these two terms are both real and have no relative phase. What in general does it do? Let me clear the screen one more time and just make some final comments about that. In general, if we have a state Ex, Ey coming in, we are always, with a half-wave plate, going to get Ex negative Ey state on the way out, even if Ex and Ey don't have the same phase. So in the linear case, as we've been doing here so far, if I had, as we've said, a cos theta sine theta state on the way in That's linear. We have a cos theta sine theta state on the minus sine theta on the way out, which can be thought of as a linear state oriented at the angle of minus theta. So just to say that one more time. But what if we had a circular state? A circular state, one example of a circular state would be a 1I state. We'll write a root 2 here just so it's got unit amplitude. If we send that through that same half-wave plate, we're going to get a 1 minus I over root 2 state. 1I and 1 minus I are circular polarization states, and I've clearly flipped the handedness. Even if you can't remember which one it is, I've clearly flipped the handedness of the 1I state in turning it into 1 minus I state. That's what a half-wave plate does to circular polarization. It flips the Y component, but instead of changing the orientation of the angle, it changes the handedness of the circulation. So if we were to summarize here what the effects are, I would say the effect on linearly polarized light is to reflect, which I'll sort of put in quotes, it's sort of reflect about the one axis, and in circular case it's to reverse handedness. And these two effects on circular and linear light are the two things that half-wave plates are most known for. As you twist the half-wave plate and you change where the one axis is, you change how much angle the light reflects about. You could have it not affected at all. It could reflect, you could align the input polarization with the half-wave plate one axis, and then the reflection is through an angle of 0. In general, the reflection is through an angle of 2 theta. So whatever angle the input light and the one axis make, it will rotate through 2 theta. Circular light, very different. In the case of circular light, the effect is very different. The circularly polarized light, no matter whether it's right or left-handed, when it comes out of the wave plate, it will have reversed to the other-handedness. There's no sense of a 2 theta rotation. Instead, there's a reversal of the handedness. And these two effects can be used for very practical purposes. Half-wave plates are much more rarely used to act directly upon elliptically polarized light. Elliptically polarized light, you would typically use a quarter wave plate, as you'll be seeing in a different tutorial.